Suspension polymerization is a heterogeneous, free radical process that disperses water-insoluble monomers in an aqueous phase using mechanical agitation and stabilizers to form spherical beads, commonly used for producing PVC, polystyrene, PMMA, and a variety of ion exchange resins. In suspension polymerization, drops of a monomer-containing phase are dispersed in a continuous liquid phase, and polymer is produced inside the drops. Suspension is a heterogeneous mixture of two immiscible phases, for example, mud in water. A solid phase suspended in a liquid constitutes the suspension. Larger solid particles are dispersed in the liquid dispersion medium. The solid particles are large enough to settle at the bottom. In most suspensions, polymer is formed via a chain reaction mechanism that includes the following steps: initiation, propagation, and termination. Organic peroxides are often used as initiators. The monomer-soluble initiator and monomers are dispersed as droplets in water, forming independent miniature batch reactors that yield solid polymer beads upon completion. Control of drop size and drop stability during polymerization is important for suspension. Drop stability depends largely on the nature of the drop stabilizer or suspending agent. Water-miscible polymers, both naturally occurring and synthetic, are often used as drop stabilizers. Polyvinyl alcohol, gelatin, starch, and methyl cellulose are used to stabilize the droplets and prevent coagulation. Adsorption of stabilizer molecules on the outer drop surface can reduce the interfacial tension and, hence, lower the energy required for drop formation. In many cases, the average drop diameters and final average particle sizes lie between 10 and 100 micrometers. Still, larger diameters might be achieved if the polymer particles are used directly as beads. In most industrial suspension polymerization, agitated batch or semi-batch reactors are used, and the continuous phase is aqueous. That is advantageous because the process is often exothermic, and good heat transfer from the reactor is required. The ratio of surface area to volume is relatively high for small drops, so that the rate of heat transfer to the aqueous phase is high. Although drop viscosity may increase substantially, the overall viscosity of the suspension is usually much lower than that which is encountered in the equivalent bulk polymerization. Consequently, agitation of the reactor contents is possible, and heat transfer via the aqueous phase to the reactor wall is good. Suspension polymerization is particularly useful when the final polymer is required to be in the form of small beads, which often have the same size distribution as the drops from which they are formed. Suspension polymerization method is inexpensive and environmentally favorable. Reaction temperature and viscosity of the medium can be under control. The product can be easily isolated as it is insoluble in water. The disadvantages are that you can use only water-insoluble monomers, and the product also should be water-insoluble. The agitation of the reaction mixture should be continuous, and the product form is not 100% pure. Emulsion versus suspension polymerization. Emulsion and suspension polymerization are both heterogeneous, free radical, water-based methods used to produce polymers, often with high heat control. Suspension polymerization creates large, suspended beads, 10 to 1,000 micrometers, using monomer-soluble initiators and droplets, whereas emulsion polymerization creates tiny, stable particles, 0.05 to 1 micrometer, using surfactants, water-soluble initiators, and micelle formation. Similarities. Technique. Both are heterogeneous polymerization methods. Medium. Both typically use water as the dispersing medium, continuous phase, to facilitate efficient heat transfer. Initiator. Type. Both commonly utilize free radical mechanisms. Stabilization. Both require agents to prevent the coalescence of particles/droplets. Key differences. Suspension polymerization involves polymerizing large, suspended monomer droplets, often resulting in spherical, bead-like products that are easy to filter. Emulsion polymerization uses surfactants to form micelles, creating much smaller polymer particles that form a stable latex, emulsion. Suspension uses monomer-soluble initiators, while emulsion uses water-soluble initiators. Typical products of suspension polymerizations are PVC, polystyrene, and PMMA beads, which require separation, washing, and drying. Typical products for emulsion polymerizations are paints, coatings, and adhesives, often used directly as latex.